Hello, everybody. It's good to be back. Today, I'm going to talk about the sine law and the so-called extended sine law, which you may have not seen before. So here's a typical triangle, and it's labeled in the usual logical way, which let me review that for a minute. So I labeled the vertices A, B, C. And opposite to A, I have the side A over here. And opposite B, I have the side B over here. Opposite C, I have side C. And I label the angles. Either I can call the angles by capital A, capital B, capital C, but just to make it, different from the vertices, I'll call it alpha, beta, gamma. So A correspond with alpha, B, beta, C, gamma. Now, this is very important because so many problems in geometry begin with this kind of labeling. And if you do this kind of labeling, well, then your geometry work is going to make a lot of sense. And if you label it some other way, it's going to be a big mess, as you will see in a minute. Okay, so in high school, we all learn about the sine law. And let's write that down. So that's A over sine alpha. So the side A corresponding to the angle alpha. And this is equal to B over sine beta. And this is equal to C over sine gamma. Okay, so it makes beautiful symmetrical sense when you label this triangle this way. Alpha, beta, gamma, A, B, C, this way, with opposite corresponding. Big B, little b, big C, little c. Okay, so it makes perfect sense. It's very beautiful when you write it. Perfect symmetry. And if you label your triangle some other way, it's going to be a mess, and you'll never be able to remember the sine law. Okay, so this sine law, we learned this in school. And we never ask ourselves, okay, they're equal to each other. This equal this, but they are equal to what? I mean, they have to be equal to something, right? Yes, they're equal to each other, but what are they equal to? See, that's the thing, that we never ask this question when we were in school, and teachers never really talked about that. But that's very interesting, and I'll show you why. Look. If I say x equals y equals z, that's all very nice. That tells me a lot. But if I say x equals y equals z equals, for example, 2, well, this tells me much more. Okay, so that extended sine law, the extended sine law that we're going to look at in this video is actually this. I'm telling you now what these three terms are actually equal to, and that makes the sine law a lot more powerful. Around any 3 points, I can draw a circumscribing circle. So I can draw a circle through A, B, and C. And if I do that, I get a circle with radius r. It has a center somewhere. It could be in the middle of the triangle, or it could be outside of the triangle. And this is our extended sine law. A over sine alpha is B over sine beta, and this is equal to C over sine gamma. And this figure, okay, in this figure, this R, this is what our terms are equal to. It's 2r, the diameter of this circle. So we have this incredibly beautiful extended sine law, which you didn't learn in school. They never told you what those three things are actually equal to. Well, they're equal to the diameter of the circumscribing circle around the triangle. So that's very interesting, and we want to prove this, actually. So our job in this video is going to be to prove this. And later on, probably in the next video, or one coming up very soon, I'm going to do some applications of this extended sine law. It's much more powerful if you know what these things are equal to, because, the competition problems and Olympiad problems and so on are designed in such a way that it would be a lot harder if you didn't know this. Okay, they often assume that you know the extended version of the sine law. All right, so let's get to proving this. Before I begin the proof of the sine law, I want to talk a little bit about Thales's theorem, or Thales's circle theorem. He's got a triangle theorem too, but we want the circle theorem. So suppose I have this chord like that, and this divides the circle up into two arcs. There's this one here, like this, and there's a big one, and we'll see what happens with the big one shortly. But let's look at the small one first. So if I have a point P here, and I draw lines, these lines intercept this arc, and this arc is an angle, so we can call that angle alpha. And if I move this point anywhere else, like for example here, P prime, well, it intercepts the same arc. And Thales was the guy who discovered that because it intercepts the same arc, it can be proved that this is also alpha. So no matter where I put P on the circle, on this side of the circle, on this side of the on this side of this chord, okay, then the angle remains the same. And apparently he was very, very happy when there's some story associated with improving it, So, okay, now let's look at a different case. Let's say we have our chord is here. Now this angle P intersects this arc. This is the big arc, you see? So it's not quite the same situation. If I put now my point P prime on the other side, well, this does not intercept the same arc. This intercepts the smaller one, you see? So P prime intercepts the smaller arc, and P intercepts the bigger arc. So what's going on here? Well, if I give this alpha, name alpha, then this will be 180 minus alpha, because, well, you could prove it yourself. You can think about it. One way to look at it is that the cyclic quadrilateral, the opposite angles are like this. They're supplementary. That means they add up to 180. Okay, so that's one. You could try proving this from basic principles. Maybe I'll do it in another video. It's very interesting, actually. So one other consequence of Thales's theorem is like so. If I have a chord line that's actually a diameter line, well, then I have a very special case. This is going to be exactly 90. And any other such point, let's say here P, any other such intercepted angle that intercepts this is going to also be 90. And even on the other side, because 180 minus 90 is 90. So if I put P prime prime here, this is also 90. So in fact, we're going to, I don't want to erase my circle. So in fact, we're going to use all three of these ideas for our proof. And I think you've seen this before, but it's good to review this. Like everyone knows this one. Some people actually don't know this one, and everyone knows this one. So it's important to know all three of these things. So this is what we will do. We will take pairs of vertices. So A, for example, let's do A, B. This will give us gamma. C. You see, C correlates with gamma. And we'll take the pair BC, and this is going to give us alpha, an expression for alpha. And then there's one more. There's AC. And AC, okay, that's missing B, so that's going to give us an expression for beta. Okay, so let's do these in order. So we'll start with BC. We'll process this one first. Okay, so BC, and we're looking for something involving alpha. Okay, well, what we're going to do here is that we are going to connect B and C through using a line through the center. So let's see if I can draw this freehand. Okay, that's not so bad. Okay, there we go. Right, so we draw a line through the center like this. Great. And this angle here is alpha. But by Thales' theorem, this angle also must be alpha. Let's give this point a name. Let's call this D. So the angle at D must be the angle at A, and that's alpha by Thales. Because they both intercept this arc. Okay, so there you go. Now this is R and this is R, so that whole line is 2R. And also by Thales' theorem, this angle B at B, so angle DBC is 90 degrees. Why is it blue? Okay. DVC is 90 degrees. Okay. Okay. So that's interesting. So now because we have a 90-degree triangle, we can do some trigonometry. So let's look at angle alpha. What is sine alpha? Sine alpha is opposite over hypotenuse. And what is the hypotenuse? That's 2R. But what is opposite? The opposite side is this one. It's opposite angle alpha in this 90-degree triangle here. And this side is A. It's opposite big A vertex, so that's little a. So A over 2R. Well, that's very good. So we have A over sine alpha is 2R. That's really nice. That's our first one done. Okay, so we've done this. Now let's do beta. And I have to copy some figures, so I will set that up here. So beta is AC. Okay, let me try to remember that. Okay, so hang on. All right, so we're going to try to get an expression for beta, and we'll use A and C to do this, A and C. So we'll draw a straight line through the center. Okay, so let's how should I do it? Okay, I'll do it starting from C. So something like this. Oh, not very good, but okay, let me try better. Yeah. Freehand drawing is so hard. Okay, that's good enough. All right. Okay, and this point is E, let's say. Okay, so let's think this over now. Well, this is angle beta, and by Thales' theorem, this is the intercepted arc. It's the same arc in both cases, here and here, so this must be true. Both are beta. So angle E and must be equal to angle B, and this is beta by Thales. And also by Thales, where is it? Yeah, here. This is got to be 90 because this from here to E to C is a diameter line. So also by Thales, the angle EAC is 90 degrees. So because we have a 90-degree angle, let's do some trigonometry. Sine, hold on. Sine beta equals what? Well, it's not obvious what sine beta is if I'm looking at beta over here. But because of the magic of Thales' theorem, I can look at beta over here, and suddenly, yeah, I can derive an expression for sine. See, that's the beauty of what we're doing. That's why we're constructing this line through the center like that. Okay, so it's opposite over hypotenuse, and where is that? Okay, opposite is B. So the angle opposite here, beta, opposite to beta is B, and the hypotenuse is R plus R, so that's 2R. So this is B over 2R. Okay, so you see where this is going? So we have we have B over sine beta is 2R. There. Beautiful, beautiful. We have number 2, part 2. Okay, so part 3. What's part 3? Okay, we did this one. Okay, beta. Now gamma. Gamma is AB. So I need to put another diagram down and do this all over again. Hang on. Okay, so now let's try for gamma. And gamma we should be able to get by looking at A and C. All right. No, not A and C, A and B. A and B, because if there's no C, you get gamma. That's how the symmetry works. Okay, so A and C. So we'll draw a line. Okay, how about here? A and B, A and B. So, okay, let's draw a line through the center from B. Okay. Okay, like that. Okay, and connect it to A, as we've been doing. Follow the same recipe. Now, let's look carefully. This is gamma. This is side C here, little c. And this must be gamma by Thales theorem, and this is point F. So by Thales, again, by Thales, a super powerful theorem, angle F is angle C. And this is gamma. And this will allow us to calculate the sine because, again, by Thales, because this is a diameter line through the center, okay, this angle here, which angle here? This one must be 90. All right, so let's write that down. So angle BAF must be 90 by Thales. Great. Okay, so we are able to write the sine now. Sine gamma is opposite over hypotenuse. So that's C over hypotenuse is 2R, and C over sine gamma, this is equal to 2R, and we're done. Okay, or it seems that we're done. So let's connect them all together. We have A over sine alpha. This is what we found. B equals B over sine beta. And this is C over sine gamma. And that's 2R. Okay. So you think, well, we're done. Well, yes, I mean, conceptually we're done. This is true. However, unfortunately, there can be odd effects when, for example, the center is not in the triangle, not inside ABC, triangle ABC. There could be some odd effects, and in the next segment of this video, I'm going to show you some of those odd effects, and we will take care of them with Thales theorem and a little bit of trigonometry, and we will prove every possible case. So here let's look at a different case. Now the center is outside of the triangle, and here we can have some different behavior that we have to be careful about. So in this case, we're going to have something odd happen with angle beta. So to find angle beta, or to find the sine of angle beta, we will look at AC. So we have to draw some line through the center. So let's draw, starting from A, And this is going to be my D. And that's a line here. So that's C. Now we see the problem here. Let's use color. Angle B intercepts this big arc here, while angle D intercepts the smaller one here, or slightly smaller one. Actually, is it smaller? Yeah, it's smaller. This arc, angle B intercepts this arc, yeah, all the way here, right? Okay, hang on. I've got a. Let me try to draw that better. So, okay. So let's talk about it again. Let's go through that again. Yeah. So angle B intercepts this big arc all the way from here through D all the way to C. Okay, because it's defined by that chord here. Whereas angle D intercepts the green arc. It's the chord here, but it's on the other side. So according to Thales' theorem, remember Thales' theorem, it had that part too. This is beta, this is 180 minus beta over here. Okay, great. So it looks like the sine law doesn't work, so it's all screwed up now. No. Okay, let's see if we can salvage the sine law. So sine 180 minus beta, what's that? Well, this is R and R, okay, and that's my hypotenuse. So it's opposite divided by hypotenuse. Okay, so what is the opposite? The opposite is B. This is side B. So it's B divided by 2R. Okay, and I get B over sine 180 minus beta, like this, is equal to 2R. And that looks bad, but actually it's not so bad. So, okay, but as an exercise for you, you work out alpha, the sine of alpha relationship, and that's going to be from BC. And beta, you can work out beta. That's going to be, well, we just worked out beta. So you want to work out gamma. That's from AB. Okay, so you do these. So this is an exercise. And I'm telling you right now, like I worked it out, and it gives you the same thing as we had before. So the only odd one out is sine of 180 minus beta. That's the oddball one. So I get from all of this sine I get A over sine alpha equals B over sine 180 minus beta, and that's equal to C over sine gamma. So you can establish this yourself. You as an exercise, you find these relationships, and these are all equal to 2R. Now, is this the same thing? If I get this sine 180 minus beta, is it the same thing as sine beta? Well, I hope so. So sometimes I'm going to get a sine 180 minus beta. Is there a way we can justify this? Is there a way we can salvage this? Yes, I'll show you. I just need to get a figure, so hang on. Here I have a plot of sine. This is sine of x. Let's call it x. Sine of x. And let's look at this carefully. So sine 180 minus beta. Let's write that better. 180 minus beta. This is minus sine beta minus 180. Okay, because sine is an odd function. Now, this is a shift of origin. So origin O shifts to the left. When you're subtracting something, the origin shifts to the left. It shifts by 180. This is pi. So my new origin is here, O prime. Okay, so what is this function? Well, this function, if I put my origin here, this function actually looks a lot like sine, except it's upside down. So what I actually have here is minus sine x. So this is minus sine x. So what we've shown here is that sine beta minus 180 is minus sine beta. Okay, and this implies the following, that, okay, sine 180 minus beta, this is minus sine beta minus 180, but this is minus sine beta, and that's sine beta. So yeah, it's true. So let's write it nice and neat over here. Okay, so sine 180 minus beta is sine beta. Actually, like everyone, well, maybe you already know this. I mean, anybody who knows trigonometry kind of knows these relationships, But it's good to be able to prove it yourself, okay? And this is how you do it. See, just sort of change it into this form. If you change it into a form f of x plus or minus some a, then you're shifting the origin left when you subtract, and plus you shift it to the right when you add, okay? So this is shift of origin. This is one way to look at it. You can also look at it as a shifting the graph itself, but I think this is maybe better to think of it this way, okay? And this, in fact, if you learn this trick, you just think about what I just did here, you'll be able to find these relationships, these kind of relationships. You'll be able to prove many of them. If you forgot on a test, you can reprove them. Just draw some figures and do some shifts, okay? So we've done it. It's true. We've finished the proof. The sine law, extended sine law, is done. It's a beautiful theorem, okay? And I like it very much. And I'm going to do some applications next. So if you like this sine law adventure, please like and subscribe, of course. I spelled it right this time. And leave a comment. I like comments. You can talk about mathematics. Maybe you can ask me to talk about something. If I'm able to do it, I'll try to do it. We'll see. If you have an interesting suggestion for a video or some comment like that, just let me know, and I'll see what I can do. Well, that was very fun, and I will see you next time.